Hello. Generative AI has emerged as one of the most transformative technologies in recent years. Tools like ChatGPT, DALL-E, and GitHub Copilot have pushed artificial intelligence beyond traditional analytical roles into the realm of creativity. These systems can compose stories, paint digital artwork, generate lifelike video, and even write functional computer code. What makes this moment especially exciting is not just the capabilities of these tools, but their accessibility. You no longer need a background in advanced mathematics or computer science to explore and harness the power of generative AI. Unlike discriminative AI, which classifies or predicts by distinguishing among categories, such as recognizing whether an image contains a cat or a dog, generative AI seeks to create new data that resembles the training data it has learned from. It doesn't just identify patterns, it produces novel outputs such as text, images, audio, or code. The distinction lies in purpose. Discriminative models answer questions like, "What is this?" while generative models address, "What could this look like?" Two foundational technologies underpin many generative AI systems today: large language models and diffusion models. LLMs such as GPT, Generative Pre-trained Transformer, Palm, and Claude are built upon the transformer architecture and trained on vast corpora of human language. Their core strength lies in their ability to model complex patterns in sequences of words, enabling them to generate coherent and contextually relevant text. On the other hand, diffusion models, which are commonly used for image generation, operate through a different mechanism. These models start with random noise and iteratively refine it into a recognizable image, guided by patterns learned during training. Systems like DALL-E, Midjourney, and Stable Diffusion exemplify this process, using deep learning techniques to translate text descriptions into high-quality visual outputs. A critical component of generative AI is the method by which it selects what to generate next. When producing text, for instance, a model might predict one word at a time. The choice of which word to output is governed by sampling strategies. One of the simplest methods is greedy sampling, where the model always selects the word with the highest probability at each step. While this often results in grammatically correct text, it can also lead to repetitive or unimaginative output, as the model lacks variation in its choices. To introduce diversity and richness in generated content, more sophisticated techniques are used. Top K sampling restricts the model's choices to the K, most likely next words, and randomly selects from this subset. This introduces an element of randomness while still maintaining a focus on probable outputs. A variation of this is top P sampling or nucleus sampling, where instead of a fixed number K, the model selects from the smallest set of words whose cumulative probability exceeds a threshold AP. This method dynamically adapts to the confidence of the model, allowing for a better balance between creativity and coherence. Another important concept is the way users prompt or instruct these models. In zero-shot learning, the model is given a task without any prior examples, relying solely on its general knowledge to perform the task. For instance, asking an AI to summarize a passage without any indication of how summaries should look. Few-shot learning, on the other hand, involves giving the model a few examples of the task along with the request. This can significantly improve performance, as the model draws from the demonstrated patterns. Some models are also capable of in-context learning, where they adapt their output style or approach based solely on the structure and examples provided in the input without any parameter updates or retraining. Text generation is one of the most prominent and mature applications of generative AI. At its core, it involves training large language models to predict the next word in a sequence, enabling them to construct sentences, paragraphs, and entire documents that read as though they were written by humans. These models, such as GPT, Generative Pre-trained Transformer, are trained on massive datasets that include books, articles, websites, and other written sources. Through this training, they develop a nuanced understanding of grammar, style, tone, and even domain-specific knowledge. Earlier versions of text generation systems, including the original ChatGPT and other GPT-3-based models, were trained on fixed datasets with a knowledge cutoff. Users would often see disclaimers like, "My training data goes up to September 2021. This meant that the model could not provide updates about recent events, evolving technologies, or newly published research. These models were excellent at reasoning and generating coherent responses, but they were disconnected from the current state of the world. This limitation has now been largely addressed by combining language models with real-time web access. Many modern AI chatbots integrate search engine functionality alongside text generation. This hybrid architecture allows them to retrieve the latest information and synthesize it in natural language. For example, ChatGPT, with web browsing enabled, can now look up current data, articles, and live events. Other tools like Perplexity AI are explicitly designed as search-augmented AI assistants. They retrieve, cite, and summarize information from up-to-date online sources. Getliner similarly integrates summarization and intelligent search to provide streamlined, web-based content discovery. In this way, text generation has moved beyond the limitations of pre-training, becoming a dynamic process that fuses statistical learning with real-time data access. As this fusion deepens, these systems are becoming more than just conversational. They are evolving into intelligent, up-to-date research assistants capable of engaging with the world as it changes. Another popular application of generative AI is image generation. The evolution of AI-generated images began with one of the most influential breakthroughs in machine learning, generative adversarial networks, GANs. Introduced by Ian Goodfellow in 2014, GANs work through a game-like structure involving two networks, a generator and a discriminator. The generator attempts to create fake images, while the discriminator tries to distinguish between these and real images from the training set. As the two compete, the generator becomes increasingly skilled at producing realistic visuals. GANs gave rise to some of the earliest and most impressive examples of synthetic media. From highly detailed human faces to creative transformations and artistic filters, GAN-based systems demonstrated that machines could produce original images that fooled even human observers. However, despite their success, GANs had limitations. They were notoriously hard to train, suffered from stability issues, and often failed to represent the full diversity of the data, a problem known as mode collapse. In recent years, these limitations have led to the rise of a more powerful alternative, diffusion models. These models generate images by starting with pure noise and then gradually refining it through a learned denoising process. This reverse diffusion technique is not only more stable to train, but also excels at capturing complex structures and textures with remarkable fidelity. A common approach involves using a vision language model like CLIP, contrastive language image pre-training, which maps both images and text into a shared embedding space. This allows the system to align a text prompt, such as a futuristic cityscape at night, with corresponding visual features. The diffusion model then reconstructs an image through iterative denoising, guided by this alignment. A common misconception about these AI tools is that they function as a kind of digital collage maker, cutting, pasting, and reassembling parts of existing artworks. This is not how they work. Generative models do not copy or retrieve images from their training data. Instead, they learn statistical patterns, styles, compositions, and aesthetic features from large datasets and then generate entirely new images from scratch each time. Each output is synthesized through millions of mathematical operations that interpret your prompt and translate it into a visual form. In that sense, generative AI is not mimicking existing art. It is creating new art informed by what it has learned. Tools like Adobe Firefly, DALL-E, Midjourney, Stable Diffusion, Ideogram, Flux AI, and Recraft are based on diffusion or related architectures. It is noteworthy some of the above, such as Midjourney, is proprietary, while some of them, such as Ideogram, is less transparent about its architecture, and thus people just speculate that they are diffusion-based. Among the various tools available today, Recraft stands out due to its use of vector-based graphics. Unlike traditional raster images, which are made up of fixed pixels and degrade when scaled, vector graphics are composed of paths defined by mathematical equations, lines, curves, and shapes. This means that an image generated in Recraft can be resized infinitely without any loss of quality, making it ideal for logos, icons, illustrations, or any visual that needs to appear crisp across different formats, from mobile screens to large posters. Video generation is one step beyond still image generation. It builds upon similar ideas but introduces the dimension of time. Tools such as Synthesia, HeyGen, Colossian, Flyke, InVideo, and Pictory leverage template-based approaches or trained video models to animate content, often combining text-to-speech, avatar animation, and background transitions. These systems are increasingly capable of producing short videos suitable for education, marketing, or entertainment without traditional filming. Generative video has rapidly evolved from simple text over stock templates to sophisticated systems capable of rendering realistic, high-fidelity scenes purely from natural language prompts. At the forefront of this evolution is Sora, OpenAI's state-of-the-art text-to-video model. Sora has drawn significant attention for its ability to generate highly detailed, temporally coherent video clips up to a minute long. Unlike earlier tools that struggled with object permanence, physics, or realistic motion, Sora demonstrates a robust grasp of spatial reasoning, camera movement, and dynamic interactions. It can generate complex scenes that involve multiple characters, consistent lighting, and even subtle environmental effects. However, OpenAI is not alone in this race. Google's Video Poet also presents a powerful generative video framework, albeit with a different emphasis. Video Poet is designed as a multimodal model that integrates text, audio, and visual data, and is particularly good at tasks like text-to-video, audio-to-video, and even video in painting. While it may not yet match Sora in terms of photorealism, its versatility and multi-input design open new creative possibilities. Meanwhile, several emerging contenders from China may soon rival or even surpass Western models. In particular, Kuaishou and ByteDance are investing heavily in creative AI, positioning themselves to compete in this space with real-time video generation engines integrated into social media and mobile apps. In 2024, Kuaishou introduced Kling, a video generation tool built on diffusion-based transformer architecture, DIT. The following year, in 2025, ByteDance released Goku, a cutting-edge AI model designed for both image and video generation. Goku is based on rectified flow transformers, a refined architecture that enhances the smoothness and accuracy of generated outputs by optimizing the flow of information within the model. Further, AI-enabled website generation has been changing the landscape of web content building and management since 2020. For over a decade, WordPress has reigned as the gold standard in website development. Originally launched as a blogging platform, it evolved into a full-fledged content management system, CMS, and is used by 22.52% of the top 1 million websites. However, with the rise of generative AI, a new class of website builders has emerged, aiming to automate the entire process. Instead of manually writing HTML, CSS, and JavaScript code, the webmaster simply answers a series of questions about the website's purpose, target audience, and design preferences, such as layout and color scheme. In just a short time, the website is automatically generated and ready to use. Platforms such as Wix AI Builder, Hostinger, Squarespace, and Framer AI, now allow users to generate entire websites simply by describing what they need. The AI can assemble the layout, generate text content, select color palettes, and even recommend images, all within minutes. This radically reduces the entry barrier for entrepreneurs, freelancers, and small businesses who need a web presence but lack the time or expertise to design from scratch. These platforms trade fine-grained control for speed and simplicity. They are designed for immediacy. You answer a few questions, and a sleek site appears. Some tools, like Durable.co, even pitch themselves as a website in 30 seconds. And they're not just visual. Many AI website generators include basic SEO setup, contact forms, and analytics by default. They tend to supplement rather than replace the manual workflow WordPress users are used to. Nevertheless, WordPress is actively adapting to AI and integrating it into its ecosystem. One of WordPress's enduring strengths lies in its advanced performance features that many newer AI-driven tools still lack. For example, features like infinite scrolling and lazy loading allow websites to dynamically load content as the user scrolls without requiring page reloads. This creates a smooth, continuous browsing experience. Sometimes this appears as a Load More button that expands the current page to reveal more content. These techniques are especially useful for media-rich websites or content-heavy blogs, improving both performance and user engagement. In modern software development, AI has emerged as a powerful assistant, not to replace programmers, but to enhance how they work. Tools like GitHub Copilot, Amazon Code Whisperer, ChatGPT, and others now support developers by analyzing natural language input and suggesting corresponding code. These assistants are trained on vast repositories of open source code and documentation, which allows them to understand common programming patterns and syntax across multiple languages. They excel at writing boilerplate code, handling routine tasks like setting up API routes or database queries, and generating unit tests or documentation snippets. In many scenarios, they feel like highly responsive autocomplete systems, but smarter, capable of writing entire functions or modules in one go. This makes them especially useful for repetitive or well-understood coding patterns. However, the current generation of AI assistants has significant limitations when it comes to building complex software systems. While they can assist with small scripts or isolated tasks, they often struggle with architectural decisions, cross-module consistency, edge case handling, and system-level reasoning. They don't understand the full scope of a project, nor do they possess the ability to plan across multiple files, adapt to evolving business requirements, or maintain coherence in large code bases. AI suggestions can sometimes appear plausible, but turn out to be incomplete, inefficient, or even incorrect upon closer inspection. This is why, despite their growing intelligence, AI tools are best viewed as junior coding partners, fast, eager, and sometimes brilliant, but still in need of human oversight. Complex problem-solving, system design, debugging tricky issues, and ethical considerations remain firmly in the realm of human developers. In this collaborative future, programmers don't just write code, they also guide and correct AI, shaping its outputs toward useful, maintainable software. For now, and for the foreseeable future, human creativity, experience, and responsibility remain irreplaceable in serious software engineering. But those who embrace AI as a coding assistant will likely write better software faster. In addition to generating text, images, videos, and code, generative AI powers a wide range of other applications, including creating presentation slides, composing music, summarizing articles, and enabling real-time translation and interpretation. As generative AI technology continues to evolve, we can expect an expanding array of innovative use cases that significantly enhance the efficiency and effectiveness of our workflows. As these generative systems mature, they are increasingly integrated into commercial workflows. From writing marketing copy to designing graphics and automating reports, generative AI enables new forms of productivity. Creators can monetize outputs by offering AI-assisted services, building customized AI tools, or leveraging automated content generation for social media and branding. Looking ahead, the future of generative AI promises even more integrated and multimodal experiences. Models that can process and generate across text, images, video, and audio are becoming increasingly capable. Furthermore, agentic AI systems represent a new frontier. Agentic AI systems are advanced artificial intelligence platforms that can act autonomously, make decisions, and adapt to changing situations with minimal human oversight. These systems are designed to handle complex tasks such as strategic planning, multi-step automation, and dynamic problem solving. Equipped with these generative capabilities, these agents may be able to conduct research, manage projects, or coordinate digital tasks on behalf of users. As access to these technologies becomes more widespread, a growing number of tools aim to empower individuals without technical backgrounds. The democratization of AI means that students, artists, entrepreneurs, and researchers alike can engage with and shape the future of this technology. In conclusion, generative AI marks a profound shift in how we interact with machines, not as passive users, but as co-creators. By understanding its principles and appreciating its possibilities, we begin to see not just what AI can do, but what we can do with it. Thanks for watching. I hope this introduction sparked your excitement about the possibilities of generative AI. This is only the beginning of a much larger journey, one filled with imagination, innovation, and discovery. People around the world are still discovering new ways to apply AGI in all kinds of fields. How might you use it to enhance your daily life or boost your productivity? I'd love to hear your thoughts.